today what we're going to start to talk about is more the sort of macroscopic quantum phenomena that occurs both in the ground states and as excitations in material and matter systems. Okay, so the first step in this will be talking about the quantum mechanics of lattice vibrations. Which is sort of the natural extension of what we covered in yesterday's class and what you worked on in the tutorial into the quantum world. And again, in principle, this can be a very difficult problem. Again, it's like a problem with infinite complexity, right? You have all of these coupled real space modes, if you want to call them that we've learned how to solve with a Fourier transform or a normal mode analysis. Which is really just taking sort of a highly interacting, highly coupled case in real space and turning it into a non-interacting or a decoupled case in Fourier space, which lets us solve it with sort of the easy methods we dealt with last time. So now in quantum mechanics, what happens is, the position vector or the displacement becomes an operator, as does the momentum. So there's an operator and its conjugate. So this thing I was calling U, maybe it's the displacement of an atom in a plane. This is an operator. P, which is just, well, you know what it is. It's mu dot, classically. So what we have to do is we have to basically go through our same derivation that we started last class and put in all the quantum mechanics. Okay? And the language of this becomes sort of complex very quickly, but it can be simplified if we just remember what we learned, I guess, in undergraduate physics about independent harmonic oscillators. Because really what we're studying is somehow a harmonic approximation, right, which we introduced last time, to the vibrational modes in a crystal, right? And so we already know how to handle vibrational modes quantum mechanically if we just have a single oscillator. And that language that we learned in introductory quantum mechanics is the language that we'll continue to use even in the many-body system, in the quantum many-body system. So the simplest model of quantum lattice vibrations was considered actually by Einstein, who was a pioneer of a lot of the concepts that we use in condensed matter, in addition to all of his work on relativity and so on. And that was just, treating each, if you want to call it atom or each object on the lattice as an independent oscillator. So what Einstein said is, I don't know if that's actually a quote. So consider each atom on the lattice as an independent oscillator. So what independent means is it's just an oscillator that is coupled to its spatial position and not to the neighbor. Okay. And if we take the linear approximation or the harmonic approximation like we did last time, which remember comes from the Fourier transform of the potential, right? So not the Fourier transform, sorry. The Taylor expansion of the potential. So if you Taylor expand the potential out, right, the second order term, the x squared term, is the linear approximation or the harmonic approximation. So in the linear case, this Einstein Hamiltonian would just be a kinetic term. Okay, so I've just written in terms of a momentum, which is an operator. And then 1/2 kx squared, which is that second order term in the Taylor expansion. So I'm going to write it as, I'm going to write it with a angular frequency. Yeah, and then my position u. Okay, so that's just another way of writing 1/2 kx squared, as you know from your simple harmonic oscillator. And that omega e is just taken to be a constant. So this is some number of independent oscillators. Actually, if we're considering a lattice and a three-dimensional simple cubic configuration, there's n atoms in that lattice. But there's also 3 spatial dimensions. So just like we had different modes before, there's actually 3n independent oscillations that can occur. So that's sum over r. I actually need another index, which is a sum over, say, lambda, where lambda goes from 1 to 3. Right? Because each oscillator can be, x, y, or z, and there's n of them. That equation's already decoupled. It's already independent. Each oscillator is already independent. Right? This spatial position here only depends on its lattice position. And so we already know the solution to this. So we learned this in quantum mechanics when we did the single harmonic oscillator solution. We introduced creation and annihilation operators. So that's creation. That's an annihilation operator. And then we can write the Hamiltonian. It's a sum over r. And now this creation and annihilation operator, which is exactly the ladder operator that you learn in quantum mechanics, there's one for every atomic position. So maybe r. And there's also one for every dimension or mode. So I can put that lambda down there. And I have to make sure I sum over that. So this Hamiltonian can just be written like this. And remember, there's a plus a half. So you remember how to do this. You write the position and you write these creation and annihilation operators in terms of the position and momentum operators. And you get this Hamiltonian. And all we've done now is summed up a whole bunch of independent terms that have this form of the simple harmonic oscillator Hamiltonian. And of course, we can introduce a number operator. Okay, so let me say and of course, these A's, A dagger and A, are operators. There's usually no confusion. But in order to distinguish N as an operator, which is just A dagger A, I put a hat on it. And that tells us that we're working in a certain basis, right? The number basis. So we have an energy associated with this Hamiltonian. We have a number basis. So instead of a position or momentum basis, we're in a number basis. And the concept of this number basis becomes important in many-body physics in condensed matter. Although here it's really simple. Right? So the eigenstates of the number operator and of the Hamiltonian are just a set of integers, you know. So I can write that set as a basis state, as a ket. So that's a number for particle 1, which is at position 1. Particle 2 at position 2. Particle whatever n. And this lambda again goes from 1 to 3 for each of these at position 3. So now instead of talking about the position or momentum of the lattice, whatever, atom or electron or whatever we're thinking about, we're talking about a quantum mechanical particle that's excited on that lattice position, right? And it's just a quantum harmonic oscillator, right? We can excite this quote-unquote particle or quantum number to any of the quantum levels allowed by the solution of the Schrodinger equation. Okay, so just a different basis. And the creation or annihilation operators, because they're labeled by a position, right? They create or destroy an excitation at that position. A lambda R destroys it. Right, and you know how this works. It raises the number from 0 to 1 to 2, or back down again if it's A. And these things also commute. Well, I should say they have a commutation relation that tells us that they're bosons. So A at R and at R prime, right, it's just delta R, these are vectors, say, R prime, delta, lambda, lambda prime. Okay, so we're creating an excitation at a specific lattice site, And we can interpret this as creating a particle, a quantum mechanical particle. Because what is a particle? It's just a quantum number, right? And so here we have a quantum number, the quantum numbers of this Hamiltonian. And this sort of way of viewing the excitations in a system is called second quantization. So this is like sort of trivial example of second quantization. So this A dagger and A create and destroy a localized excitation. It's localized that lattice site, and it's called a phonon. This is like a simple example of a phonon, which is meant to, bring some connotations of photon to the surface. Right? So a lot of this theory is tied to the history of considering statistics of photons.
Completion number basis, shouldn't that go from R1 to Rn, but each Rj has lambda 1, lambda 2, and lambda 3?
Oh, this is supposed to be n here, actually. So each position has lambda 1, lambda 2, lambda 3, or x, y, z. So I actually don't need a label on those lambdas, probably. But I meant to say that there's a lambda for each position. And I meant to go to n, not to 3 there. So it's just that these operators can act at every site, one at every site, right? And there's 3 dimensions. And if you're in a 2-dimensional system, then there'd only be 2 lambdas, right? 1 and 2. It's just remember, it's like the longitudinal and transverse modes, except we don't have any, we're not dealing in k-space quite yet, because this is a totally decoupled problem. Okay, and we call this the number, the occupation number, how many phonons sit at that site, and so on. Okay, so this model is like, it's not even an actual model of a solid. You'll barely reproduce any physical features that you would see in a real material, except sometimes it's used to model that optical branch. So that optical branch that you worked on yesterday has a relatively flat dispersion. So even near k equals 0, that thing's some constant. And so it's just like this thing is approximately constant. But it fails to capture the behavior of that linear dispersion relation that happens in the acoustic branches, say. Okay, so it's not a bad approximation in this case, but we want to construct something more general.
So when we talked about the optical branch yesterday, it involved a K. So if we don't have any coupling between the sites, how do we define that?
So there is no K here, right? So the optical branch it had some slight K dependence, but I'm saying if you approximate it by a flat band or a flat branch, that's your Einstein phonon. But I want to introduce the K right now. Okay? So this is just to introduce, and this is just a review of second or third year undergrad quantum mechanics, where you had the ladder operators, the raising and lowering operators. So where does the K dependence come from? So it comes from the fact that the displacements are coupled, right? In the same way that they were coupled in the classical case, remember? We had U of S and U of S minus 1 or U of S plus 1, right? And so the Hamiltonian will have this, it'll be this difference equation. So.
Can you please elaborate on in what sense we're, by exciting into higher levels, we're producing 2, 3, 4, etc. particles? Like when you have the one harmonic oscillator, you have the same particle going to higher energy excitations. Now, by applying the creation operator, we don't have higher energies of the same particle. We somehow have more particles.
Well, it's like you have a particle of of a different type. So if you excite, I'm just talking about real space. So if you excite a particle into the first excited state on site I, then you can imagine you excite another particle in site J, site K, or something like that. That's what I mean by different particles. They're all localized to the site. So it's not a very good analogy in that sense. So if you can have particles also in higher excited states. But it's going to make way more sense in K-space to talk about particles. So what we're going to do now is write a Hamiltonian that's coupling the oscillators in their neighbors. Then we do a normal mode analysis. And then those phonons have a sort of better definition in K-space.
Applying a dagger of R and with lambda at the same site twice would give you the same one particle in the first excited, second excited.
I would say I think that's a good interpretation. Yeah. And then so there's 3n possible, basically, lattice sites and modes or particles, and they can be in different states.
Yeah. So when you say you have created 2 particles, they're at different positions.
Yeah. So that's how the equation's decoupled. So now when the real space equation's coupled and I decouple it with a Fourier transform or a normal mode analysis, I have 3n possible modes that are labeled by the k vectors and also whether you're parallel or perpendicular to that k vector. So you can imagine having 3n possible particles in that case too. So that's what, so in analogy, yeah, so now we're going to talk about labeling our particles with k and lambda, not with site and lambda.
But can you not have 2 phonons at the same lattice site? Can you not create, you can produce this 2 phonons at the same lattice site?
Not actually analogy.
With respect to that, a phonon is a collective excitation, right? Here we're talking about localized excitation. So
that's why I say they're localized phonons. So they're not the phonon. I mean, I'm just trying to draw an analogy to what you learned in quantum mechanics, but yes, the phonons that we're going to discuss right now, they're actually you consider them a long wavelength or a collective excitation that occurs in the crystal. So this is not this is just to bring some intuition to the raising and lowering operators. So the proper definition of phonon is what I'm going to talk about now, I would say. So hence the the quotation marks. So you already know where this is going. So I want to write a Hamiltonian that couples, real space lattice coordinates. So I can do that in 1D. And in 2D, let me label my sites in 1 dimension. Let me put in a mass, a particle mass. So I'm labeling the sites explicitly now, just as S. So what would I call that? U of S. So that looks more like the Hamiltonian that I dealt with last class. It's just the one-dimensional version. And you see the Hamiltonian couples adjacent sites together. Okay, and it's done in the nearest neighbor interaction. Way, and the only difference is that these things are operators now. Okay, so they're quantum mechanical operators. And we can basically solve these things in the same way. And I'm not going to go through this explicit solution because I'll just take all class. And But you already have the intuition for this from what you did classically. So in 1D, you can imagine introducing position and momentum operators that can be transformed into Fourier space. So pk, these are the Fourier coefficients, if you will, si, ksa. So I can substitute those operators in. And then I can also define, well, okay, let me write the Hamiltonian. So my Hamiltonian would be transformed to a sum over K space, 1 over 2m. Where I've been careful to label now my coefficient of my K-space U operator with a frequency dependence. Okay, so this isn't obvious. So I'll just take the easy way out, so you figure it out. But you basically have to grind through this Fourier transform. And the difference between, as you expect, the difference between this and the Einstein case is that instead of the real space modes, if you will, being decoupled, this is a sum of independent K modes, just like it was in the classical case. Okay? And the only subtlety, or the only important thing, is that that frequency depends on that K value. So further then, I could introduce creation and annihilation operators. And they're not these ones that are the creation and annihilation operators for each independent particle. They're creation and annihilation operators for a particle, a collective particle in K space, if you will. So these create and destroy, not an excited state on a real space site, but they create and destroy, a running wave, if you will. That running wave will have some momentum k, or some wave vector k. And they're this, they're made of linear combinations of U and P. And I guess I won't write that down. And then your Hamiltonian will become a sum over all of these independent K modes. A dagger, how am I labeling these things? Maybe K, AK, K plus a half. So even the complete analogy with the Hamiltonian and the uncoupled Hamiltonian in real space, now it's uncoupled in K space through this normal mode analysis. And this is worth doing like once in your life, and then never again. And also, I've only summed over wave vectors k. But remember, there's actually another index that has to do with how many modes per wave vector. So I should also have a lambda here. Okay, so I forget what I call these. It's like the branch or the polarization. That's the thing that has, there's 3 acoustical and 3 minus P optical, 3P minus 3 optical for each. For, P atoms in a unit cell. But we're only dealing with 1 atom per unit cell here. Okay, so in analogy to what we did in the classical case, the energy of each, so now we have phonons in K space. So this A dagger and A are phonons in this sort of collective language. Do you have a question?
So the 3 acoustic branches and the 3P minus 3 are both 3D, right? Space.
Yeah.
But you're working 1D, right?
Oh, well, at this point, let's change things to 3D. There. Yeah, so I just wrote that equation in 1D, right? But this is 3D. So you'll decouple modes in all those directions. But yeah, good question. Other questions? So we'll talk about that. Yeah. So that that is the crux of the matter. How do you calculate omega k, depending on what problem you have, right? That's actually the difficult thing. And then what thermodynamic signatures do you get from that omega k? So h bar omega it's like the energy of that mode, right? Of that k and lambda value. And that's how you label your phonons now. So these are labeled by. Okay, so that real space picture is sort of gone. And we're thinking of things that, for example, in the long wavelength limit are similar to these long sound waves that you can imagine, sort of propagating through a medium. And keep in mind, just like before, h bar times k is not a real momentum in this normal mode analysis. It's a lattice momentum. Or a crystal momentum. Okay, so all I've done is written down essentially a Hamiltonian. So now the question from a condensed matter perspective is, what are the macroscopic thermal or thermodynamic effects of this quantization? And so what I want to show you now or convince you of is that when you have this type of quantum mechanical Hamiltonian, the thermodynamic effects that come out of that are quite different than what we would expect classically. And this is important. We're all past the stage where we don't believe in quantum mechanics. But at some point in the history of mankind, there's important questions about how much quantum influenced the classical world or the macroscopic world. And phonons are one of the first experimentally realized manifestations of this quantum world. And in particular experiments such as the specific heat. So the temperature dependence of the specific heat of any crystalline solid, should show some sort of manifestation of these quantum mechanical particles. And in fact, it does, and it's a very clear signature. And so you might argue that historically, just doing this type of simple analysis and realizing that there's some quantum mechanical nature to the operators or in the Hamiltonian led to one of the most important experimental tests of quantum mechanics. Okay, so each phonon, will have some probability of being excited thermally. Just like on the lattice case, you have to put some energy in the system to jump this, jump from the 0 occupation to the 1 occupation to whatever. So you can imagine this energy coming in thermally. And now what we're doing is exciting phonons of a label k and lambda, right? Right, and that, if you will, excitation spectrum is by construction the excitation spectrum of the harmonic oscillator. That's how we've constructed it here. So what is the total energy of all the phonons that are excited at a given temperature? If we can answer this question, then we can predict through the derivative what the specific heat of all the phonons looks like. So to construct this thing, I'll call it U. What we want to do is sum over all of the possible modes h bar omega k times the expectation of having n number of phonons in that mode. So that's just a number operator here. So I'm just taking the expectation value of h. And there's a 1/2. Forget it. U equilibrium. This is the thing we have to calculate.
That U equilibrium doesn't diverge when you're in the thermodynamic limit.
It's just some constant, right? Just some sum. Oh, you mean because the sum? No. That's like the energy of the vacuum, right? Is the energy of your vacuum, the one you live in, or the one that's out in space. It's the same question. So we're talking about energy excitations out of that vacuum. So this is the expectation value of the Hamiltonian. Really? Oh, h. And what we need to do is calculate that expectation value of that number operator. Okay. So this thing, we know how to calculate that expectation value, right? So it's like a trace of the number operator. So let me label this as minus beta. Let's label this as a sum over n over the partition function. Just very sort of formally in some sense. And so what we need now is a sum Okay, so I've just labeled n's here. But so it's a sum over all n, with the energy beta h. So it's h bar omega. So I don't want to write all my labels because it's going to look messy, but these are k lambda labels here. N plus a half. You basically have to calculate that sum. Okay, so you do this, it's just a trace. You can sum over all the modes, right? The n, the A dagger A operator, operating on e to the minus beta h. That omega has the full k lambda dependence in there. And that'll give you the thermal equilibrium number, expectation value of that number operator. So that's what you need to calculate. These are bosons. Do you know what it is? Yeah, so it's like the Planck distribution. So, you can do this, but it just equals, there's no chemical potential yet. I'll talk about that. Which gives you the Bose-Einstein distribution, but this is just Planck. I spelled Planck. Just see there. Okay, so if you haven't done that before, you can work it out. But in the end, you'll just have 1 over e to the h bar omega. Maybe I'll just label them k lambda. So that's beta times that, so it's kBt minus 1. Okay, that comes from your stat mech class. That's just a statistical mechanical problem. But with it, we can access the energy of all of those phonon modes. Okay. And let's use this to calculate the specific heat, which is just, I'll say this, the specific heat at constant volume, which you remember from thermodynamics is basically just the temperature derivative of that quantity, of that U up there. Okay, does this make sense? And this is something that you can walk over 20 minutes to the basement of the physics building at UW and measure in a laboratory. Take your favorite, whatever, crystalline solid, put in one of Yankish's dilution refrigerators, and you'll get the specific heat of the sample. So what we're trying to answer here is, what do we expect based on this quantum mechanical Hamiltonian? So we can take various limits. I mean, we can either solve this in continuous space, we can take limits, we can look at high temperature behavior, low temperature behavior, and just try to sort of deduce what's going on. So let's just look at a limit first. So we didn't even look at the specific heat in the classical case. But in the classical case, we can just take a limit here of, kBt greater than h bar omega. Right? And so the classical behavior is actually contained in this, we would hope. And it actually is. So all you have to do is expand your exponential. Okay, so h bar omega and kBt is in the exponential. And this will just give me right, so I can see how the 1's going to cancel. Then again, it'll be left with h bar omega kBt. And up in that energy expression, I have an h bar omega. Okay. So then what is left? 1 is left. I took kBt on the outside. So I still have my sum, but there's nothing inside that sum. So that's just all the number of all these modes, right? It's kBt, something like 3, n, p if there's a basis. That's the energy. And so then the specific heat is just, right, this temperature derivative. It's du over dt, right? So it's just 3 n kb. And so this thing's temperature independent. Okay. And this is known before this calculation was done or before this limit was taken. It's called the Dulong and Petit law. So now let's contrast that with taking the full integral, so including the low temperature regime. So in order to do a quantum mechanical calculation, you need to know that dispersion relation, if you will. So there's all sorts of forms that dispersion relation can take. So how are we going to set this up? Well, we can at least look at another limit. So that was the high temperature limit. So if we look at the low temperature limit, we can just make a series of assumptions that's reasonable on the form of that dispersion relationship, basically, and see what we get, okay? So before I talk about those assumptions, let me just, instead of taking the limit and throwing away a whole bunch of stuff in that u expression, let me write down that full expression and make some variable substitutions. So I'm going to leave in all the wave vector dependence and everything. And the specific heat is just the derivative of that energy expression. Which somehow I can't see, so I hope I'm writing it the same. So I know I just started putting k as a subscript. And we can actually we can actually, in principle, solve this sum. Although we are dealing with sort of a macroscopic number of particles. And so it makes a lot of sense to look at this as an integral. So to take some sort of continuum limit of this. And you'll do this all the time when you're dealing with these lattice systems. Okay? So it's good to get used to the recipe for converting a sum over k to an integral over k. So let's put the vectors in here. So in principle, we can just take the sum, convert it to an integral. Imagine we're in some huge number of particles. We have all these k states that we're filling up. But we should be careful to normalize by the volume. Okay, so V is the volume of your system. So I'm assuming simple cubic. And where does that 2 pi 3 come from? I can't hear you, but it sounded right. Right. This is the volume of the Brouillon zone, right? So another way to look at it is, because remember, we're dealing with reciprocal space. So that 2 pi 3 over L, that's what you calculated Monday, L cubed. That's the volume of the Brouillon zone. So we're going to use this integral, and then, well, maybe later today or tomorrow, I'm going to use it incorrectly and show you how we miss an important physical result. But so now let's just convert this to an integral. So I got a V term. I still have a sum over these lambda modes. Well, so all of these k's should have been vectors, but let me write it like this.
Where in the sum is the volume normalization implicit or explicit?
Well, so that your k-space lattice. Say if we're talking about hypercubes or simple cubes or 1D, 2D square, 3D cubic, it has the same form as your real space lattice. But when you integrate over space, it's like you're ignoring that length scale and you're integrating over all space. So we just want to include that length scale, which is the volume that you're neglecting somehow when you integrate, which is that volume of that Brouillon zone. That's just one way to think about it.
Here to justify going from a sum to an integral, you're considering the short wavelength limit, right?
So what you're considering here is the limit where you're in a macroscopic or a massive number of particles. So it's like the resolution of your Brouillon zone is very fine. So your n is very large. And that Brouillon zone is being chopped up into, you're going from minus, say, pi by a to pi by a in n steps in your Brouillon zone. So if you have a huge number of particles, you can resolve that Brouillon zone. It's just like you're discretizing, you're resolving that Brouillon zone with very tiny little steps. And if those steps get small enough, you can integrate. Okay? And so the only thing you're missing in that integral is that lattice length scale, essentially, or that volume that that's actually implicit or explicitly defined in that Brouillon zone. So this integral now, is the thing that we want to solve. And you're going to see these integrals lots, okay? So let's make some approximations. And of course, I should write here that to be mathematically correct, that integral occurs over the Brouillon zone. So now I have a dispersion. I might have a basis that I haven't really talked about in here. And I also have this integral that only goes between, minus pi by a and pi by a or something like that. So, which again, the a comes in the limits of integration here. So let's make some approximations. So number one, I'm going to forget any complications about having a basis. I hate those things. I don't want to deal with them. So now I just have 3n modes. Let's assume a dispersion relation. Okay. Well, you have more modes to sum over. So you have those 3p minus 3 modes and all this type of stuff. So I'm not even going to talk about how to do this when you have a basis. You have to worry about it right at the step of your Fourier transform. So it's possible people do this stuff all the time, but I think in terms of sort of working through these integrals and stuff, we'll just forget about the basis. So this is all just a simple cube from our perspective. So let's assume a dispersion relation. So again, this dispersion relation has to be calculated typically every time, but I'm just going to take a linear approximation. So here's your long wavelength assumption here. Okay, so in the long wavelength limit, remember we're dealing with essentially sound waves, and those sound waves are like the acoustic branch, right? So we're ignoring the optical branch. The optical branch came in with a basis anyway. Okay, so now let's assume that we only have a long wavelength situation, and our omega is just some, I can't remember if I called it C or V last time, some CK. And we'll plug that dispersion relationship in to that integral. The third thing, I'm just going to extend the limits of integration. And this last one isn't necessary. I could restrict that limit of integration from 0, say if this is my origin, to the volume of the entire K space allowed to me by the size of the crystal, n. But let's just assume that's infinity for now, just so I can solve this integral really, really quickly. And we'll talk about where that breaks down later. So this is enough. This is enough for me to get a number out for the temperature dependence of the specific heat. Okay, questions? So the most important part of this calculation is something very simple. It's basically writing this integral. It's something we can solve in K-space in one dimension and making variable substitutions that extract our T dependence. And we're going to play this game 3 times in this class. But it's basically how you get the thermodynamic, the simplest thermodynamic behavior out of these types of integrals, if you will. And again, this is just some sort of like Planck distribution. So we can do it again for Bose-Einstein. We can do it again for Fermi. And we'll get low temperature specific heats out of this procedure. Okay, so first thing, let's use, well, I can replace my dispersion. So H bar CK. Okay, but that K is just it's just like the R vector. So in spherical polar coordinates in K space, I should convert this integral to just an integral over K, just the magnitude of K, right? Not the angular dependence. So let's take that angular dependence out. And it's 4 pi K, remember? DK, no, K squared. Yeah, that's important.
When you assume this dispersion relation, you're assuming that in the three directions the velocities are the same. Right? So that the polarization.
Yeah. Yeah, so you know, if you have some angular dependence of that velocity, then you can't do this thing I just did here. Because I just integrated over all the angular components to get this 4 pi, all right? And it's the angular components in the three-dimensional Fourier space, right? Or the K space. I mean, if this seems confusing, just step back and think, you know, this is a highly coupled set of equations that we can solve with an integral to a very good approximation as long as we're dealing in K space. That's why I said in condensed matter, you're almost always dealing in K space for this reason. Now this is something you can just do. And the only important kind of trick besides, you know, all this spherical integration and stuff is just a change of variable. And the one I'm going to use here is beta h bar ck. I'm going to call that x. Okay, so I'm going to have e to the x minus 1. And I can change my k to dk to dx, and so on. And I'll get a temperature dependence because, remember, my beta is just Boltzmann constant times the temperature. And that temperature dependence is what I want to look at. I want to look at the temperature dependence of the specific heat. Okay, so this is something you should do more than once in your life. So I'll just write out all the terms so you can. And then my dk, right, so I need to have dx, that's t. So this variable substitution means I can write everything in terms of x and remove the t and all the kb's and all those h bar c's out to the front. Okay, so give it a shot. Make sure you can get the same thing as me. Because importantly, what comes out is a partial derivative with respect to T, which is the definition of, which comes from the definition of the specific heat. Here's my T dependence here. So when you do that substitution, you got to make sure you pick up all the T terms. That's the only trick here. And then some integral here, that's just an integral over x, some fancy function. This thing I know off the top of my head. Just kidding. It's something I read in a book with pi 4 over 15. All right, so you look up that integral, and then everything else is in front of that. You take the temperature derivative, and you see that we get a T3 behavior. Okay, so therefore, specific heat it's a partial derivative. Oh yeah, sorry, I was teaching second year like differential equations, and I went through like several lectures of partial derivatives, and somebody asked me, why don't my 2's cancel? So just be aware that there's a partial derivative there. That was my lowest moment as a professor. Now I've taken the partial derivative. I have an extra KB out front. There's my T3 dependence. So it's in complete contrast to the classical Dulong and Petit law. Okay.
Which of these assumptions is motivated by the fact that you're in the low temperature limit?
Yeah, so that's a good question. So there's a low temperature limit that I can make. I should have been more clear. I can make a low temp. I can take a low temperature limit without even assuming a form of the dispersion, which would have gave me an exponential dependence. So if I just expanded the exponential out, but in this case, it's only the fact that the low temperature justifies the use of that long wavelength approximation. So I wasn't clear on that. Okay. So it's more like I have a high temperature case here, and then I've waved my hands and told you that I can use a linear dispersion, and that's kind of the low temperature assumption there. And with that linear dispersion, and the fact that I use I extend that integral, that's all that really goes into this. So it's low to intermediate. It's like the low temperature limit is t goes to 0. I wouldn't have to have done that whole integral. It might even go to 0 exponentially. You could if you ignore the dispersion. So this is like more like an intermediate to low temperature. But
so this dispersion relation is basically for a gapless excitation, right?
yeah, so these are all the acoustic modes.
What can I consider gapped excitation? I mean, so that the dispersion relation is somehow like square root of k squared plus m squared, which the ultimate place is also linear, right?
Right. So, okay. Well, yeah. So let me just draw this one first. So this is the linear dispersing case. This is T3. Then I'll answer your question. This is CV, and this is going to high temperature, whatever. 3N kV, right? That's a 3, T3. So look at another, you guys can do it. Look at another branch. So look at the Einstein. The simplest case is the Einstein case where that dispersion's constant. Okay, even though it has some sort of k dependence, you can just ignore that and say that's a constant one that doesn't go to 0. Okay, so it's not linearly dispersing. So try WE is omega E, oh, I can't believe I said W. Omega E is a constant. So will you get the same low temperature behavior? You won't get exactly a T cubed here, but you'll get something that exponentially decays and turns on. Okay, so this is exponential. And this one is omega equals C. Okay. Okay, so even if you look at one of those other branches, you'll still get a low temperature behavior, okay, that's different than the classical limit. And so that's the important point. So this low temperature behavior is, is actually a manifestation of quantum mechanics, a very clear manifestation of quantum mechanics. And so many materials, sort of at the onset of the experimental technology needed to go to very low temperatures, were seen to have basically this T3 behavior.
So, if we assume this linear dispersion relation, even in the high temperature limit, there are still going to be modes where this KBT much greater than 8 bar omega doesn't hold. So why should we expect the same high temperature limits?
So what are you saying? So even at high temperatures,
Here you're choosing KBT is much greater than 8 bar omega, but with summing over all k's, and there will be some values of k for which this doesn't hold.
oh yeah, right. So those modes do contribute up here. Okay. So the question is, do they contribute enough to modify the behavior? And basically the answer is no. It's qualitatively, it levels off to some constant, but the effective temperature that happens can be relatively high, because those modes can contribute, up to some, I don't know, room temperature or something like that. So you do, in principle, you can account for those modes in a more careful analysis. But they're not enough to give you sort of to like kill your specific heat like they do, they do in this full treatment here. So it is, we should be more careful in this analysis. So I mean, this is called like a Debye T cube law. And if you look in textbooks, the Debye treatment will also have a more careful treatment of these intermediate modes. And it's done by, being more careful with this integral in the first approximation. You can extend the limits of that integral from 0 to, the volume, the sphere of states that you have in K space for a system of size n. So you can imagine putting a cutoff in that integration and looking at, redoing this whole game and so on. But we won't do it in this class. I think the basic features, like the physical features of having some sort of classical limit, some sort of high temperature limit, contrasting with the low temperature limit that comes from the quantum treatment, is basically the only point I want to make here. Other questions on this? What am I doing here?
Does the heat capacity exactly go to 0 as you take the limit as t goes to 0?
Yeah, so
Or does it level off at something?
So it's an interesting question, actually. There's a lot of physics in that question. So this is just the contribution of the specific heat from the lattice vibrations. Okay, so maybe I construct a magnetic system or something that has degrees of freedom on that lattice. They could be electrons. They could be like just the dipole moments or something like that. Those other degrees of freedom will also contribute to your specific heat. Okay, and typically, say I'm studying a magnet and I want to see what's going on with the magnetic order or something like that. Those degrees of freedom will like conflict with this phonon specific heat. So typically what happens is there's a characteristic temperature for which this thing totally freezes out. And below that temperature, you'll see other interesting things due to electronic degrees of freedom or magnetic dipoles or something like that. And so in a real experiment, a whole bunch of modeling has to go into it to subtract off phonon contributions or subtract off nuclear contributions to the specific heat to just look at the sort of physics of interest.
So effectively, as you go to lower and lower temperatures, you're freezing out higher and higher excitation modes. But say even in the case as you go to very, very low temperatures, you're still left with the vacuum state.
So it's zero temperature in principle. Yeah, you're left with a vacuum state.
But that itself has a 0 point energy.
Mm-hmm.
So you will never, even in this case, you should in principle never really get.
Right, but the
zero.
degrees of freedom associated with that aren't accessible. So we're just looking at the specific heat due to the degrees of freedom here of lattice vibrations. Right. So it's the change in energy that's contributing to this thing. So it's the phonon specific heat. Yeah. So the phonon specific heat, it's the derivative, right?
Okay.
So that vacuum energy gets when you take the derivative, that's just a constant. Then that derivative goes to zero.
Right.
Yeah. But if you have other degrees of freedom that aren't constant, like I say magnetic or electronic or something like that, then those will contribute to your overall specific heat in an experiment. And that's very typical. I mean. So the phonon-specific heats, they're known, the behavior of these things are known very well, actually. And usually what experimentalists look at these days are more like electronic or magnetic degrees of freedom. So specific heats due to whatever crazy magnetic process might be going on. So you'll get a curve like this T cubed, and then you'll fit a function to it and then subtract it off. And the stuff that's left over is like the interesting stuff, So that's kind of how it goes these days. So I only have a few minutes left. You guys will get an assignment today. So pick that up after class. I think Dennis has it at the back. That assignment's going to be on magnetic degrees of freedom. And what we're going to do in lecture is calculate exactly the specific heat contributions due to the magnetic degrees of freedom. So imagine my lattice, and there's some sort of moment sitting on it. How will those moments give me an addition to this specific heat behavior? And you're going to look at the sort of nitty-gritty quantum mechanics of how to solve these magnetic systems in your homework. Except before I do that, I just want to take half a class and talk about another bosonic system. This bosonic system will be what the subject of your tutorial is on Thursday. Okay, and this is a Bose-Einstein condensate, BEC. Okay, so this is material that'll help you with Thursday's tutorial. And when you see your assignment today, don't panic. We're going to get to it tomorrow. But look through your assignment that's due on the 20th, and then you'll get an idea for sort of the direction that we're going in lecture. So the BEC, what is a BEC? I mean, we've been talking about bosonic, emergent degrees of freedom, if you will, collective excitations. You should imagine these particles as like, they're arising due to constraints in the system. You're highly constrained. You're like, you have a harmonic oscillator that is coupled in a very complicated way. And somehow out of this vacuum state, when you warm the thing up, you get these emergent bosons, these phonons. And these phonons can be treated essentially as particles. And those particles give you some behavior. You can also just look at bosonic particles. I mean, why? Just take some helium-4 and dump it in a refrigerator or something like that. And so those bosonic particles also have things like a distribution, right? This distribution you learn in stat mech. And you can play games like look at contributions to the energy, the number occupation, and things like that. And surprisingly, macroscopic manifestations of quantum mechanics come out of these elemental systems also. Phenomena. This is a macroscopic quantum phenomena here. Bose-Einstein condensation and its brothers and sisters are also examples of macroscopic quantum phenomena. One of the first to be discovered was superconductivity by Camerling-Onnes. I have no idea how to spell that. So, K-O-N-N. And this is way back. Superconductivity. I mean, the guy, liquefied helium. He could look at very low temperature conductivity in metals, saw that the conductivity went to 0. This is a famous story, right? This was conventional superconductivity was solved by Barty, Cooper, and Schieffer, and it must have been, I think the 50s was a Nobel Prize, so 1957. So experimentally, this macroscopic quantum phenomena that occurs in all sorts of metals and stuff was basically this, explained by a very accessible theory way back in the 50s. So what's underlying the quantum mechanics of superconductivity? Well, we're going to explore this, but we're going to explore it in the bosonic context. And another experimental system a superfluid is also a manifestation of quantum mechanics at the macroscopic scale. And superfluidity occurs in also occurs in helium-4, so occurs in bosonic systems and has all sorts of interesting properties. This has an interesting story, the discoverers of this. Alan Kapitsa, I didn't know if I wrote the last one down. I think it was Meissner. So this is around 1937. This is after the discovery of superconductivity, but before the BCS theory. Helium was liquefied and cooled to such a temperature that it was seen to go superfluid. And superfluidity is all sorts of weird things. So if you pour this superfluid helium in like a dewar or something, it flows up and around the sides of the dewar. If you stick a straw in there, it shoots out the straw. So it shoots out of the straw. So there's all sorts of weird sort of transport properties and stuff going on in superfluid helium. And this was worth a Nobel Prize. I forget when. Maybe the Nobel Prize is actually in the 30s. But one of these guys was at Toronto. I think it was Alan at the University of Toronto. And he never got the Nobel Prize. So poor guy. Anyway. So I know Kapitsa definitely did. And after the discovery of superfluidity, people actually had kind of a theory for it. And it was this theory of Bose-Einstein condensation. So Bose-Einstein condensation is essentially something that was theoretically discovered before the experiments. These are experiments by Bose and Einstein. And these guys doing statistical mechanics of these quantum systems. And this was in the 20s, so 1924. I mean, there's some interesting story there. I think Bo's going to get his paper published and send it to Einstein. Einstein got it published, no problem. Science hasn't changed. But London actually postulated that the Bose-Einstein condensate is sort of the underlying theory behind these things, superfluidity and superconductivity. And there's something to that. I mean, what we're going to see is Bose-Einstein condensates come in a non-interacting boson system, and these are very strongly interacting systems. So it's not quite the right theory somehow, but the concept is correct. And the concept is essentially that, bosons can all pile into their ground state, whereas fermions have this Pauli exclusion principle, and they're not allowed to all pile into that ground state. And that ground state, which we'll call a condensate, which is the C here, gives rise to all these interesting quantum properties. So that condensate actually comes out when we do when we take a long wavelength, or we take a continuum treatment of the distribution, the Bose-Einstein distribution, which is what we'll do next time. But we have to be very careful to capture the proper quantum mechanics in that case. So that's what we're going to do next time. And just a note on this. This was finally seen, an actual Bose-Einstein condensate in a non-interacting system with all the BEC properties. And it wasn't until 1995 by this guy, Cornell, and I think there was a second Wieman. So they got the Nobel Prize in 2001 for this. And the problem with seeing a Bose-Einstein condensate is you need a very clean system to make sure that there's no interactions and make sure that there's sort of no other effects polluting your physics, like coupling to phonons and stuff like that. And so it's actually remarkable. The first time that this Bose-Einstein condensation was seen was in an artificial system. So it wasn't in a, it wasn't in a whatever, like lead or tin or something like that, or ceramic. It was actually constructed explicitly in a cold atomic experiment. So these things I told you about, where they basically take lasers, they do this evaporative cooling on atoms, and then they make a standing wave by adjusting the frequencies of the lasers to get like a potential. They can vary that potential so that they can cross a transition into this Bose-Einstein condensation phase. So like humans are getting sophisticated enough that we can actually get enough control over quantum systems in a laboratory to realize these things, which were kind of only theoretical oddities or theoretical simplifications in some sense. And so it bodes well for seeing a lot of macroscopic quantum phenomena, I think, in the upcoming years. So that's all for today. We'll get into the BEC tomorrow. Pick up your assignment from Dennis, right? You have it back there? Yep. Yeah. And I'll see you guys tomorrow.